Yeah, welcome everybody back to DOCAS. Today it's a pleasure to have Brad Dirks from the University of Michigan, who's going to tell us how to understand the roots of B functions following Lichtin and Kashiwara.
Yeah, great. Thank you so much to the organizers for inviting me to speak in DOCAS. Yeah, today is mostly going to be preparing the background that we need to understand for like general D modules over the complex numbers for next week when we like tackle the proofs of Kashivar and Lichtin. And yeah, so next week, like what I will explain, the generalization of Lichtin's proof is joint with my advisor, Mircea Mustața. Yeah, I guess this week, this is all sort of more like expository and more like a lecture on what we need to know for D modules. Okay, so yeah, here's the setup. Is I'm gonna let X be AN, so the affine space, with some chosen coordinates x1 up to xn. You could think of X as any smooth complex variety. And I'll let D be the Weyl algebra. Oh, maybe I'll call this polynomial ring R. So that's just R, and you would join some symbols such that dxi xi equals 1. So this is the commutator of those two elements. And then these guys commute with each other. And maybe I'll actually just say that this is the Kronecker delta function. So that they also commute with the x's that are not the one which is their number. Okay, and our goal, like the D module, we have like a specific D module in mind. So I guess our goal is to understand the D module so I'll call it NF, which is going to be ds times f to the s, where f is just some polynomial in this ring R, or you could think of it as a regular function on X if you want to do it more generally. S is just an indeterminate. And so maybe I'll put it on the right half. And the D module structure is by, right, so I'm just going to tell you how these guys operate, these del X, whoops. Okay, how these guys operate. And then you just extend it using like the Leibniz rule and like taking products of this action. So dxi applied to f to the s. Oh, well, actually, I should first say where this lives. So I'll say is defined on a larger object. So it's going to be R, and you adjoin the inverse of f, and you also adjoin s. And that's f to the s. And so now these dxi's act by, yeah, I mean, really, you just want to know how they act on f to the s and then extend sort of by the Leibniz rule. So it's like the power rule is what's really happening here. So you bring down the power.
Brad, sorry to interrupt. So this f to the s is just a symbol, right? It doesn't really mean anything.
Yeah, so I'll write that here. F to the s is like a formal symbol. It just helps you remember the D module action. Yeah, so you bring down the power, you apply this derivation to that function f. And right, when you do like the power rule in calculus, you have to decrease the power by 1. So we have this f to the s, and so we have to divide by f. So this division by f is why we adjoin 1 over f into our like big sort of ambient module. Yeah, so then NF is the dxs module generated by f to the s, and it sits inside of this R1 over f to the s. Yeah. So clearly this is, oops. This is finitely generated over D of S, right? It's a cyclic module over this ring. It's just generated by this symbol F to the S. But there's a question, is it finitely generated over D? Right, there's no reason why we should be able to get like the action of S just by applying differential operators. And so the answer is actually yes, but we'll have to wait till next time to see that. But maybe I can write down one example where it is sort of clearly true. So we say F, a polynomial, is quasi-homogeneous if there exists some theta in this direct sum R dxi. So this is equal to like the tangent bundle if you were doing like an ambient, or sorry, an arbitrary smooth variety. So I guess I would call that like Tx. So we want some vector field such that theta of F is equal to F. So this is like inside the ring R. And the utility of this is that, so that implies that theta F to the S is equal to S times F to the S, right? If we look at the definition of the action on the right-hand side, so by extending this linearly so that we have those R coefficients that we need over here and taking sums, this will just be an F up top. And when we divide by this other F, we're just left with S times F to the S. And so then, yeah, since it's finally generated over D adjoin S, and we can get the S action by applying this operator theta. So then that implies here NF is finitely generated if F is, quasi-homogeneous. And I'll just say, just to be careful, which ring, finally generated over this D. Okay. And so maybe an example of a quasi-homogeneous is if F is a monomial. Then I think for any I such that alpha I is non-zero, xi dxi over alpha I applied to F is equal to F. Great. Okay. Yeah, and that's actually going to be very important for next week. So monomials are examples of quasi-homogeneous polynomials, and they're one where we already sort of know that this nice module NF is a module of interest is finitely generated over the differential operators. Okay. So now I'm going to go into more like general constructions from the theory of D modules that we're going to need for next week. And there won't be many proofs, but I will just mention the like important properties that we need for these constructions. Okay. And so, yeah, this might be review for many people in the audience, but I think it will be useful for us next week to have all the properties that we want sort of written down. So yeah, so on this ring D, we have the order filtration. So I'm going to denote that by F. And so it's just the collection of all differential operators where when I write them using that commutation relation, so that the del's are at the end, I want the size of this multinomial exponent to be smaller than that bullet there. And so these P alphas are polynomials. Where D to the alpha is D1 to the alpha 1. I guess I wrote dx1, dxn to the alpha n. And size of alpha is just the sum of the alpha i's. Okay. Yeah, so for example, f0 of D is just the polynomial ring. You're not allowed any differential operators in f0 of D. And f1 of D is, well, you have to have the last stuff, but then also you add in this extra part. like the vector fields. Ooh, I should say this is an n here. Okay, yeah. And this is also well defined for like when you have an arbitrary smooth variety. Okay, so now here's a definition. A filtration, U bullet of M of a D module by R submodules is compatible with F bullet D if when you do the multiplication, I should say when I say D module without any prefix, I mean a left D module. That's just what I'm more comfortable working with. Sorry, this should be a U. So you want it so that this order filtration moves the filtration U in like the correct way. So this is the definition here is compatible. Definition. So, oh, yeah. Oops. So if U bullet M is a compatible filtration, the Reese module, oh, sorry, I don't even need to do that. We are not going to do the Reese module. That's my bad. Whoops, I do want that part though. Yeah, so if this is a compatible filtration, it is good if, right, so we can take this associated graded module, which is just the direct sum of all these things, is finitely generated over this ring ger F bullet D, which is direct sum ger F K D K and C. Okay, and maybe here's something that I won't prove, but recall is that this ger F bullet D is isomorphic to R, and then you would join variables that commute with every element of R. So there's like no commutator relations. That's not what I wanted to have. So I'll call them like Chi1 up to Chi-n. This is a commutative ring. Okay, great. Oh, and I guess we also want U to be exhaustive here. So the union of all these UKs is equal to M. Okay, great. Yeah, and maybe I'll say these Chi are, they're the image of those dxi's in ger1 of D. Okay, great. So maybe I'll give an equivalent definition of good, which is useful if you want to write down examples of good filtrations. So U bullet M is good if and only if there exists some elements in M and some integers such that you can write U bullet M sort of as like the filtration given by the order filtration multiplied by those elements. Oops. Yeah. And so, for example, if M is just generated by a single element, U, then FIM, which is just FI dx times U, is a good filtration. But something else that we see is that because good filtrations are exhaustive, by definition, that implies that M has a good filtration, sort of if and only if M is finitely generated over D. Right, so if these elements exist such that they can describe each of these filtered pieces, like an arbitrary element of M will eventually live in one of those filtered pieces. And so, yeah, so that means that M is actually generated by those elements M1 up to Mk. And so this is actually part of why we want to know if that D module NF is finitely generated over the ring D. Okay, and if you're doing it over like an ambient complex variety, you would replace like the word finitely generated with coherent, sort of everywhere that it appears. Okay, yeah, but we should think of this GUR bullet M as a coherent sheaf on X cross A to the N. And so what do I mean by that? I mean, right, because of that fact, like GUR F bullet D is isomorphic to R adjoin some polynomial variables. Then this spec of GUR F bullet D is isomorphic to this X cross A to the N. And so we just explained that a good filtration gives you a module which is finitely generated over this ring GUR bullet FD. Okay, this is very useful because then we can look at its support as a coherent sheaf. And so we'll define that by, so it's the vanishing locus of the annihilator of this guy, U bullet M. And so you'll notice on the left-hand side, so this is called the characteristic variety. The left-hand side doesn't have the letter U on it. And so, yeah, so we'll see some properties is that, well, first of all, this subset, so this is as a closed subset of X cross A to the N. Yeah, so let me lower this. So this is, sorry, does not depend on choice of good filtration. Yeah, I guess that's what I should, I think because I'm saying, this is responding to the question in the chat. I guess since I'm saying just taking it as a closed subset, I guess one way to describe that would be like to replace and with its radical. So yeah, maybe we could do that just to be safe here. But yeah, we only want to think of it sort of set-wise. Yeah, thank you for the question. Well, okay, so this does not depend on the choice of good filtration. And two, if we have a short exact sequence, so 0 goes to N, goes to M, goes to M. Well, sorry about that. If this is a short exact sequence of D modules, then the characteristic variety of M is equal to the union of the characteristic variety of the other two pieces. And then something else that we're going to need next time, which is going to be pretty important, is that there's like this notion of multiplicities. So if Z inside of this characteristic variety is an irreducible component, then like sort of this multiplicity along Z of that subset does not depend on choice of good filtration. And also, I guess mirroring 1 and 2 on the left here is 3 and 4. If we have another short exact sequence of D modules, and if Z is an irreducible component of, yeah, I guess I should say this and this and this, then the multiplicities add. So yeah, and so this will be important later on. Okay, great. Okay, sorry about that. I need to reshare my screen, I guess. Okay.
So maybe while you do that, can I ask, so
Yeah.
do you need Z to be top dimensional? I'm always confused about this.
Yeah, I think you, I think you might. Definitely in the application we're going to use, it should be max dimension. So I'll just say of max dimension. Yeah, just to be safe.
Okay, thank you.
Yeah. Okay, great. And then finally, here's something that I'm going to write as a property, but it's actually like a theorem, which is Bernstein's inequality. And so this says that if Z is, that's M, is an irreducible component. So now this doesn't have to do with max dimension or anything. Then the dimension of Z is greater than or equal to N, which is the dimension of X, right? Okay. And so these Z's are living on this X cross A to the N. And yeah, so their dimension is always between N and 2N. I should say if M is non-zero here. Yeah, so I'll say M is non-zero. Okay, great. So maybe I'll give a definition based on this. So M is holonomic if its dimension of the characteristic variety is equal to N, and M is subholonomic if dimension of the characteristic variety of M is less than or equal to N plus 1. So it's not as small as possible, but it's just one off from being as small as possible. So let's give some examples. So this ring R with the usual D action is holonomic because its characteristic variety is just X cross 0. But then the ring D itself with the usual D action is not holonomic because its characteristic variety is this whole X cross A to the N. It's sort of the furthest thing from it. Okay, and so here's a question. Is an F holonomic? So the answer is, well, first of all, we don't know if it's coherent or not. So we would first of all restrict to the case where it is coherent. But then the answer is in general, no, but it is subholonomic. And this will be very important for next week. And we'll prove that next week. So see next week. Okay, great. Yeah, and feel free to interrupt me with any questions if there are any. Okay, and maybe one more key fact, which I will not prove, but which will be useful in the proof of existence, is Kashivar's constructability theorem. I guess I will really just say an application of Kashivar's constructability. So if M is holonomic over D, well, I should just say holonomic, then this endomorphism sheaf, we can look at the endomorphisms of M as a D module, and we can look at the stalk. This is finite dimensional for all X in X. So this is like finite dimensional over C. Yeah. So I guess, yeah, this is a key fact, and we're going to use this next week. Basically, our goal will be to show a certain module is holonomic, and then use the fact that this is finite dimensional to get a minimal polynomial of a certain endomorphism of that module. Okay, Great. So now maybe there's a new section, which is short, and it's just going to be quickly about side changing. So this ring D has an anti-involution, what I think is called the classical adjoint, defined by, so we write P as these polynomials P alpha X D to the alpha. This should map to, so we switch the order of them and we also negate the differential operators. So this is just for all alphas in this index set, and this is all alphas. This is just a finite sum. And I'm going to denote this one by P to the T. So yeah, if you wanted to rewrite it in terms of what, I don't know why it just stopped sharing. Okay, let me try again. Is it? Okay, I don't really know what's happening, but yeah. So this is the classical adjoint. And so this satisfies, oops. So if I look at the product of two elements and take their classical adjoint, that switches the order and then takes the adjoint of both of them. And also, I guess it's involution. So if you do it twice, you get P back. Okay, but now for any, well, sorry. So this gives us a right D module structure on, so I'm going to write it as omega of R over C. This is just isomorphic to R as an R module because we're just working with the polynomial ring. So this should really be R times dx1 wedge dxn. You can think of this as sort of another formal symbol if you really want to. And it acts by, right, if we have some element in here and we do P times it on the right, then we do the transpose of P times this coefficient G, and then we keep along this guy. Yeah, and I want to phrase it in terms of the this top degree differential forms, because next week it's looking at it this way will help us choose like a distinguished element. Sort of like the relative canonical divisor is going to give us a distinguished element when we view it in this way, even though we might have like trivializing coordinates like we do here. And it's called side changing because given any left D module M, the tensor product, so I want, yeah, well, MR is going to be denoting this omega R tensored over R with M, has a right D module structure. Just by, so we can say like these dxi's on some omega tensor M is equal to omega dxi tensor M minus omega tensor dxi little m. Yeah. And so we could phrase this all because of this trivialization. We could phrase it just in terms of how it acts on elements of M, but it will be important next week to sort of take along for the ride this differential form here. Yeah, and then we just extend the rule to all of the and linearly to non-elementary tensors. Okay, and so I think the last general thing that we need to understand is push forward of D modules. And I'm really just going to give the definition and like the one property that we are going to need next week. So yeah, so one reason to side change is that it's easier to define push forward for right D modules. Okay, so for this, we're going to need something called the transfer by module. So if f from x to y is a map of like smooth complex algebraic varieties, or maybe like a map from an to am, let d from x to y, this sort of helps us remember which side has which module structure. This is just going to be the pullback as ox, or as like as modules of the differential operators downstairs. Yeah, so this is a morphism of varieties. So we have this, and this is so the x is on the left, so it's a dx comma f inverse dy bimodule. Yeah. And so now we can define the push forward. So given a right D module M, define, so I'm going to use F plus. I've also seen it, so maybe if you've seen this before, this is also known as like this like integral symbol. But what you do is you do the derived push forward along F of M tensored over D of X with this transfer bimodule. Right, so over here we're saying it's a left dx module, so we can do this tensor. But because it is a bimodule, we have this lasting f inverse dy action. And so by adjunction, when you do this push forward, you pick up so this is a complex of dy module. I mean, really, it's like an object in the derived category, but however you're going to represent it is going to be by a complex.
Sorry, Brad, and should the tensor over dx be left derived? Or?
Yeah, sorry, that's exactly right. This should be the left derived. Yeah, great. Yeah, okay, so maybe I'll just give an example and not show why this gives the right answer. But if we do an inclusion of a point into A1, right, so D modules on a point are just C vector spaces. And so let's look at how to push forward just C. This is like, this would come from something by like, I mean, this is studied when you look at something called Kashivar's equivalence. This is really just C adjoin differentiation in the x direction if the coordinates here are x. And like the way that the D module action is, so this is a right D module. So I think it should just be D mod XD. Right, so I should say this is really, the point that I'm talking about is 0 here. But we can talk about D modules on that point 0 just as C vector spaces. So a one-dimensional C vector space pushes forward to this, and then you can extend it by additivity. But here it's an actual module, and this does not happen in general. In general, it's pretty hard to understand. Well, I guess I should say in general, not very easy to understand. And the main theorem we're going to need is, so if f from x to y is proper, which is like some condition that closed sets map to closed sets and some other things, then m or and m is coherent over dx, then all of the cohomologies of this object in the derived category are, well, yeah, I should say coherent over dy. All right, so when we take cohomology, we do get a dy module. And so we can talk about, is it coherent or holonomic and stuff like that. Yeah, so what we're going to need next week is proper maps,
Brad, maybe
sort of preserve coherence. Yeah.
Oh, sorry to interrupt. Maybe just a comment about the example, because I think in this seminar, a lot more people might be more familiar with another description of this module, which is the first local cohomology of Cx supported on X.
Yeah.
The I plus C.
Yeah, I think this also looks like you do like Cx, X inverse mod Cx. Is this right? Yeah.
Yeah.
Yeah, sorry, this,
And
yeah. That's a good
And
comment.
then I also seem, maybe I'm misremembering, but I thought this is not placed in degree 1, in homological degree 1, but rather, sorry, not placed in homological degree 0.
Does there?
Yeah, anyway, maybe I'm misremembering.
Okay, yeah, so maybe that's right. So I guess this has one one non-zero cohomology, and whichever one it is, this is what it is.
And it's that one. Awesome.
Yeah.
Thank you.
Yeah, you're welcome. Thanks for the question. Okay, great. So now we can finally get to the specifics of like this module NF. So this section will be about B functions. Okay, so definition. The Bernstein Sato or Sato polynomial. So maybe I should remember. So we have F, that's a polynomial here. And D is that R adjoin differential operators. Yeah, so the Bernstein Sato polynomial of F is the monic polynomial of least degree, satisfying this relation. So we're working inside of that module NF. So yeah, so I should say, yeah, this thing on the left. So this is in C of S. This is equal to some differential operator times F to the S plus 1. So this thing is in D adjoin S. So this equality happens inside of this module NF. Yeah, just so that we can like be specific on what it means for these two symbols to be equal. Okay. Yeah, and so this is
sorry,
for
Brad, let me interrupt you once again. Sorry. So this F to the S was a formal symbol. So maybe it's good to clarify what F to the S plus 1 means.
Yeah. So this is just F times F to the S. Yeah, thank you for that. I should have been more careful.
And then maybe since it's been a while, so can you remind us what NF was?
Yeah.
Thank you.
And so this NF was just DXS times F to the S. So this is like that DXS module that's generated by this this one symbol. But like a priori, we don't know if it's finally generated over the ring of differential operators. Okay. But we can give like a restatement sort of in more, I don't know, in some D module terms. So restate this as, right, we have this operator NF to NF, which is called T, which sends something of the form PS F to the S maps to PS plus 1 F times F to the S. So really this is just S maps to S plus 1. Like that's how you should think about it. Because this is just F to the S plus 1. Yeah, so this satisfies T times S equals S plus 1 times T. So they don't commute, these two S and T's, but they almost commute. And so another definition of the Bernstein-Sato polynomial is BFS is, this is denoted BFS. Yeah, and so I think by specifying its monic, I'm looking for a non-zero polynomial. So I should say, I'll just say non-zero here to be careful, but yeah. So this BFS is the minimal polynomial for the S action on the quotient, which I'll call MF, which is NF mod TNF. And so like a remark is that this S action does descend to the quotient. So this TNF is a DXS submodule because S times TNF is equal to T times S minus 1 NF, and that's contained in TNF. Oops, I don't know what happened. I can't write it because of the button. Okay, I'll move everything over a bit, I guess. There we go. Yeah, and so this thing that we're modding out by is stable by the S action. So we get an induced S action on the quotient. Yeah, and this is the view that we're going to take next week. But so maybe I'll give some examples of Bernstein-Pseudo polynomials. So the first one.
Sorry, Brad. Yeah, well, sorry, I interrupt you once again. But
that's okay. Yeah.
This TNF also is also dxs applied to f to the s. Is that right?
I think it might be like dxs applied to f to the s plus 1.
Oh, right. So
yeah, I think they're isomorphic, but maybe we need to be careful about this sort of thing. Yeah, I should say, right, so this t does this. So this is the linear.
I mean, it seems to me that this t that you wrote would be all of dxs times f to the s.
Yeah. Yeah, I think the image should be exactly, yeah, because you could always just sort of plug in p of s minus 1 and you would get, yeah. Yeah, so maybe I'll comment. Image of t is dxs f times f to the s. Yeah. Okay.
Thank you.
Maybe I'll give, yeah, you will. So I'll give some example of, well, these are really more, the first one's a property, but okay, so another remark. So if f is not a unit in R, then yeah, BFS is divisible by s plus 1. So to see that, we have this relation. And if I plug in -1, I get BF of -1. F inverse equals P of -1 times, well, 1. Because if I do F times F inverse, I would get 1. But this right-hand side lies in R. So the differential operators multiplied by 1, they kill them, but they have some coefficients that should be like polynomials in R. And this is, okay, so I should really say like the action. So P of -1 is in D, and then D times 1 is contained in R. So if BF inverse non-zero, then we can divide by it. It's just a constant, and that would mean F inverse is in R. So yeah, if it's not a unit, this number has to be 0, which is pretty useful. That gives us an example of a root which is negative and rational, and we'll see in all of these examples. So that's how the roots look. So if F defines a smooth hypersurface, then BF of S is equal to this S plus 1. So when I say a smooth hypersurface, I mean like none of its partial derivatives don't all vanish at the same point in a to the n. And so I guess the proof is, so we can just sort of let F equal x1 by doing some change of coordinates because it defines a smooth hypersurface. And then if we just hit x to the s plus 1 with the differentiation, we just get s plus 1 times x to the s. So this says BFS divides s plus 1, but then by part 1, we know it's divisible by s plus 1 also. So we get equality. And then maybe one example where we get an interesting Bernstein-Pseudo polynomial is this sum of squares function. So then actually BFS is s plus 1, but then there's also an s plus n over 2. Right, so we know that okay, so maybe I should say there's a fact which is that 2 is an if and only if. Converse also holds. And so we know that this sum of squares thing, it's singular at the origin. So all of its partial derivatives vanish when all of the x's are 0. So there should be some extra term that isn't s plus 1. And if you use like the sum of squares differential operator, then yeah, you will see that like this polynomial does satisfy the relation that we need for a Bernstein-Pseudo polynomial. So yeah, because it can't equal s plus 1 and it divides this, it has to equal this polynomial. Okay, and I'll give one more example next time, which will be like probably the most important thing for next week's talk. But maybe just a note is that all the roots are negative and rational. Right, so here we have, okay, well, ignoring case 1, that's like -1 is the only root, and that's negative and rational. And then these two, -1 and negative n over 2 are both rational. And this is not a coincidence. So I didn't just choose polynomials that would give us this. This is like what we're going to prove next time. So we'll prove a stronger version of this next time. Okay, great. So am I supposed to go until noon, or was I supposed to stop at 11:50?
You can keep going until noon if you want.
Okay, yeah. So I think it might be good for me to actually prove the existence today, so that I have more time to get through the shape of the roots argument next time. Yeah, I should be able to do all this in 13 minutes, and then we don't have to review so much next time. Okay, great. Yeah. Well, are there any questions while I pull up this part of the notes?
Yeah, maybe let me ask something I was a little curious about. So you said that in example 3, the Bernstein-Pseudo polynomial cannot be s plus 1.
Yeah.
What was the reason?
Yeah, it's because you have this sort of like, if the polynomial equals s plus 1, then the function has to be smooth.
I see. So this 2 is like an if and only if. It's not just an if.
Yeah. Yeah. So this BF, like it's non-equal to s plus 1 is sort of a test for if your hypersurface is singular or not. Yeah. And so since this one is singular at 0 or the origin, it can't just be this term. And we can write down a relation that makes it divide this whole polynomial. So I think by degree reasons, it has to equal this polynomial.
I see. Thank you.
Yeah, you're welcome. Okay. Yeah, so let's run through the proof of existence. So this will be...
Uno es ruso y otro es alemán. No sé quiénes son. Mamá, yo no te he enseñado a cruzar.
Sorry, Jack or Luis, could you mute that person?
Oh. It wasn't a question. Okay.
I think, yeah. Anyway, sorry about that.
Okay. So yeah, let me just do proof of existence. Okay. Yeah. So we're going to actually assume something. We make the following assumption. So I'm going to star it because I'm going to refer back to it later. So this says that yeah. When I was saying it's a fact, I guess I should have said it's like a not very easy to see fact. Yeah. Yeah, there might be easier ways to show that 3 is the actual Bernstein-Pseudo polynomial. But yeah, okay. So I want to assume that the vanishing locus of all of the partial derivatives, I mean, really, I don't want to even phrase it like that. I'll just say the set of points where each partial derivative is 0 is contained in just the set of points where f equals 0. I don't even know what I wrote here. Oh, the following assumption. So this can always be achieved in a neighborhood of this set where f equals 0 using generic smoothness on the target. But we'll see that this is actually pretty useful for when we move forward. Yeah, and so we can always make this true by replacing x with a neighborhood of f equals 0. And since we're interested in like a local study of f equals 0, like the singularities, this is sort of a harmless replacement to make. But this assumption will be very useful for us. Okay, and now to begin with, we'll also assume f is quasi-homogeneous, so that this nf, which is this dx s f to the s, is finitely generated over D. Okay. Right, remember this was sort of the only case we were able to write down where we know that for sure. Okay, so now let's make a lemma. So under these assumptions, NF is subholonomic. Right, so remember that means the dimension of the characteristic variety of NF is less than or equal to n plus 1. So the proof is we can, so maybe this is also a fact that I won't show, but if we look at this thing, which is the sum of all submodules of NF, such that their dimensions have this property, this is a coherent D submodule of NF. Okay. And then also, if we look at this open subset where f is non-zero, so in particular by our starred assumption, none of the partial derivatives are 0. So by star, f, I mean really it is smooth, like it can be, f can be like used as a coordinate. So we can write f x2 xn as a system of coordinates. So really what I'm saying is there are these other functions such that dxif equals 0 for all I between 2 and n. Okay. But then also that means, right, dxi f to the s equals 0 for all 2 is between I and n. And so, right, that sort of means if we looked at this in x cross a to the n, like those last n minus 1 coordinates are all 0 on this characteristic variety. So like CHNF is contained in chi2 equals chi n equals 0. And so that means its dimension is less than or equal to n plus 1 over this subset f equals, or f is non-zero. And so really what that means is if we look at the quotient nf mod L, this is supported on f equals 0, right? Like this nf is one of these things in the definition of L. Like it is one of these guys that satisfies this if we restrict to this open subset where f is non-zero by this argument here. So if we look at r times f to the s, like this symbol, so the r module generated by this symbol contained in nf over L, this is a coherent r module which is supported on f equals 0. So that implies it's killed by some f to the k. This is like a Null-Stellensatz type thing for k greater than or equal to 1. And so that means f to the k times f to the s is in this module L. But L is a D submodule, so that means dx f to the k times f to the s is contained in L. And so that means that this characteristic variety of dx f to the k times f to the s has dimension less than or equal to n plus 1. But then just using this like t to the k from nf to dx f to the k f to the s, this is an isomorphism. And so that finally implies the result that we wanted. So we get that this NF is subholonomic. And now we're actually almost done. So yeah. Okay. Yeah, so now we can say that MF is holonomic. Remember, MF is NF mod T NF. And so the proof is its characteristic variety is contained in the characteristic variety of NF. So its dimension is at most n plus 1. Okay, if it has a irreducible component of, so this is an irreducible component of dimension n plus 1, then that implies that, right, so we want to show that it can't have any such irreducible components. But if we look at 0 goes to NF by T, goes to MF to 0. This is a short exact sequence. Then the multiplicity argument says MZNF equals MZNF plus MZMF. But that really says MZMF equals 0. So it can't have any irreducible components of dimension n plus 1. So all of its irreducible components must have dimension basically equal to n, because so it is holonomic. Because we have this upper bound here. Well, like, yeah, this forces the dimension inequality. Okay, and maybe I will just right now say, okay, so then corollary is if F is quasi-homogeneous, then BFS exists. Proof. Right, so I guess, yeah, I'm going to end today with just showing in the quasi-homogeneous case that we've been working with, BFS exists. And then we'll start next time by proving that this implies it in general. Okay, so the previous lemmas imply MF is holonomic. And then this Kashivar constructability implies that the endomorphisms of MF, dx is finite dimensional over C for all x in X. Okay, but S is one of these endomorphisms of MF, right? Remember, MF was the quotient by this T, the image of the map T, and S sort of preserved that sub guy. So S is a D-linear endomorphism of this object. So at least at any point, S satisfies a minimal polynomial. So I'll say at any point x in X. But then, right, we can say like X is quasi-compact. And so by taking like the LCM or just the product of these for finitely many points corresponding to some open cover, this BFS exists. Take LCM or product. Okay, so yeah, so we can see how all those things that we started out today with came together to prove existence of the B function, at least in the quasi-homogeneous case. Yeah, so I think I'll stop there. Thank you guys for listening.
Thanks, Brad, so much. Do we have any questions for Brad? Okay, so maybe I'll start it off. So this corollary actually seems what you're proving is really for any holonomic D-module, any endomorphism is admits a minimal polynomial. Is that right?
Yeah, I guess it's sort of probably, right? The proof should work no matter which endomorphism I choose.
Yeah.
So yeah, I think you're right. As long as it's a D-linear endomorphism of a holonomic guy.
Oh, I see. Also, in this Kashiwara constructability, so is it very hard to prove then, or is it?
I think I don't know. I've never actually read through a proof. I think there is a proof in that green book, HTT.
Mm-hmm.
But yeah, I haven't actually looked through a proof, so I don't know how difficult it is.
I see. Yeah, it seems pretty strong. Okay,
Yeah.
Thank you so much.
Yeah, thank you.
Any other questions? Okay, if not, then thank you, Brad, once again for a great talk. And before we let you go, let me mention something. So, yes, you might know, was it last week or 2 weeks ago, there was the Mathematical Congress of the Americas in which Jack and Luis organized a session on differential operators on commutative algebra and algebraic geometry. And the talks for this session of the MCA have been made available for free online on the YouTube channel of CIMAT. So I think, Luis, if you could share the link to the talks. Yeah, so if you're interested in seeing what went on in that session, and maybe there's some talk there that could strike your fancy, then I invite you to check it out. Okay, so that's all for announcements. We'll see you all next week, and Brad will continue on this topic. Thank you.